Let's discuss lecture number 8, that is under same evolutionary process. It is 4b. Now you see, this is the figure 61. Just we have taken an application as drones, and the figure 62 represents the proposed design. You can see there are 4 modules. So module A, module B, module C and module D. Module A is again a 2 by 2 array. Module B is again a 2 by 2 array. Similarly, module C and module D. All 4 modules are identical and independent. So that means they are not connected with each other, but they are again identical. That means the resistance is identical to each other. Now, you can see the same thing in figure 63. There are 4 switches, which SWA, SWB, SWC and SWD. So what happens is, let us suppose this is a drone. If it is landing on module A, then SWA will be activated. If it is landing on B, then SWB will be activated. And similarly with C and D also. So in this way, we can actually mitigate lateral misalignment problem. Also, we can achieve this stable efficiency, stable induced voltage. So there are multiple advantages with this particular design. Now also one more thing, you may also get a doubt that in the literary works there is a similar kind of work. There are 4 coils overlapping with each other. So like what is difference with this? Now if you see, the problem with that literature design, because we are comparing all results with that design only, with that design is their uniformity of voltage is not uniformity, or we say the misalignment tolerance is only 32.4%, compared to what we are achieving in this design is almost more than double than what they have achieved with reduced dimensions. So we also reduce the dimensions drastically. So the advantage is miniaturization, enhancement of the uniformity factor, because we have used not the uniform voltage, uniform magnetic field, but rather we have used the non-uniform magnetic field distributions using in this particular design. So figure 64 shows the layout of the diagram. So this is the layout. So you can see this is 241. It is somewhere the entire dimension is 428.1 only from starting to ending. Whereas the literary design, which you have seen in the literature books, module A, module B, module C and module D1, it is actually 700 millimeter. So the dimensions are huge compared to what we were proposing. Now in figure 65 you can see the complete difference. You will understand. There they are actually forming the uniform magnetic field, but here we are forming the non-uniform magnetic field. You can see this is the module A magnetic field strength. So when the receiver coil is actually positioned in the region 1, I mean let us say the module above the module A, then the magnetic field you can see as follows, as figure 65A. And if it is landing on receiver coil B, the transmitter coil B, then you can see the magnetic field will be activated this part. So similarly C and D. So the corresponding induced voltages also you can see. So when it lands on module A, then induced voltage is actually uniform like this. Then if it lands on B, again you can find the induced voltage is constant in that region. So in this way, virtually you can understand that in the entire receiver coil region you can achieve the constant induced voltage with the help of the switchings by actually activating only 25% of the transmitter coil. That means you are controlling, you are reducing the 75% of the flux leakage. Now this is the detection system that we have proposed. Now these are the what we call as rectina coils. These are the rectifier detection coils. You can see coil AB, coil CA, coil DC and coil BD. So only 4 coils are sufficient to actually detect the position of the receiver coil, whether to activate transmitter module A or B or C or D. We can determine using these 4 detection coils only. How? I will explain that clearly. First I will explain you why the positions of these are placed in these locations. For that I will go back. Now you can see because we have produced the non-uniform magnetic field, there are void regions. Void regions means the regions where the magnetic field strength is very low. So this is one of the void region you can see, which is very low. So if I place the detection coil in this region, what happens is it will not it will not be disturbed with the transmitter coil's field strength, or I say that there will be no cross interference between the transmitter coil and detection coil. So the performance of the detection coil will not be disturbed by the transmitter's magnetic field strength when it is positioned in these void regions. So that is the main purpose why we have positioned in these regions. These are the void regions of the magnetic field strength. So number one, now how we are detecting the position of the receiver coil is, let us suppose my receiver coil is just above the transmitter module A. Then what happens is, because it is just above the transmitter module A, the detection coil AB and CA receives the reflected what we call reflected induced voltages on the due to the receiver coil on these detection coils. So these detection coils, that is CA and AB, will receive same amount of induced voltage, rectina voltages compared to BD and DC. These strengths will be greater because my receiver coil is positioned above these two locations. So as these two are greater than these two, so the readings of VAB and VCA would be greater than VTH1, and whereas VBD and VDC would be less than VTH1. Then we need to activate SWA on. So similarly we will do for other switches also. So this switching states of the receiver coils is only for the when the receiver coils are staying within those modules. Let us suppose there is another possibility, that is when the receiver coil is actually landing in between transmitter module A and B. Let us suppose initially it is in transmitter module A, because of some problem it has been misaligned towards module B and it is landed in the center, that is between transmitter module A and B. Then what happens is, my detection coil AB will receive the maximum induced voltage compared to all the three induced voltages. That's the reason VAB will be greater than or equal to VTH2, and the other two, that is VCA and VBD, will be same because these two will act as same when it is over this, and obviously VDC will be very low. So then we have to check whether my previous state is what if let us suppose if switch 1 was previously on, now as it is moving towards module B, we have to activate SWB, and we have to off SWA. So if previously module B is on and if it is moving towards module A, then we have to do the reverse one. So in this way we need to store the previous data, and we have to compare whether it was previously it is moving from module A to module B or module B to module A. Accordingly we have to activate the transmitter module. So this is the figure 68 denotes, this is the experimental setup. You can see we have used the Litz wires. So there are 4 modules. So module A, module B, module C and module D all are overlapped with each other, and this is the receiver coil, and we have evaluated the S parameters using the VNA and this robotic setup. Figure 69 also denotes the signal generator and amplifier and Arduino controller based setup to test the detection system. See, with VNA you can't test the VNA's detection system. The reason is VNA generates very low power, but even although signal generator also generates very low power, but we have an amplifier, so it amplifies to a very high power, so that we can see the detection system properly. So by using this Arduino controller, and what we have done is we have activated the relay. We have activated the transmitter modules based on the detection coils. So you can see the detection coils also. These are the detection coils, 4 detection coils. You can see over here. So figure 70 is actually the threshold voltage states of the detection coils. So using this figure 70 only, we have written a program on the Arduino controller so as to activate a specific transmitter module based on the position of the receiver coil. So the misalignment tolerance of the proposed modular multi-coil antenna in terms of uniformity factor is 75.5%. You just imagine, from 32.7% of the previous literary design, we have enhanced to 75.5%. Not only that, it also reduces undesired magnetic field by 75% compared to all the previous designs. And the proposed design, whatever we have proposed here, is so far the best misalignment tolerance along with best leakage controllability using the switching circuit and detection coils. So it is the combination of what we have got in the optimal non-uniform magnetic field strength and a switchability of the coils is resulted the best possible design. So the conclusive demerits, the only limitation is obviously because we are using detection systems, switching circuits and Arduino controllers, complexity will increase and also the cost will increase. So with this, the end of lecture 8. Now we will go on to the lecture 9, which is based on the receiver coils in the next lecture. Thank you very much.